This lecture will explore Cloud Spanner. Cloud Spanner is a fully managed, mission-critical relational database service. Cloud Spanner is ideal for relational, structured, and semi-structured data that requires high availability, strong consistency, and transactional reads and writes. Example workloads are trading systems, insurance, gaming, and e-commerce-like ticket sales. Cloud Spanner offers strong consistency, including strongly consistent secondary indexes, SQL support with alter statements for schema changes, and managed instances with high availability through transparent, synchronous, built-in data replication. Cloud Spanner offers regional and multi-regional instance configurations. For any regional configuration, Cloud Spanner maintains 3 read-write replicas, each within a different Google Cloud Platform zone in that region. Each read-write replica contains a full copy of the operational database that is able to serve read-write and read-only requests. Spanner provides the best of both worlds. Typically, relational databases provide a schema, SQL support, and strong consistency, but lack in high availability and scalability. And on the other hand, schemaless NoSQL databases like MongoDB provide horizontal scalability, that is, billions of rows and high availability of the data, but they lack the schema. A Cloud Spanner database can contain one or more tables. Tables look like relational database tables in that they are structured with rows, columns, and values, and they contain primary keys. Data in Cloud Spanner is strongly typed. This means you must define a schema for each database, and that schema must specify the data types of each column of the table. Data from related tables are interleaved to improve performance. Cloud Spanner divides your data into chunks called splits. The start and end keys of this range are called split boundaries. Cloud Spanner automatically adds and removes split boundaries, so the number of splits in the database keeps changing. At a high level, all data in Cloud Spanner is organized into rows. Rows are split, and Cloud Spanner creates multiple copies or replicas of these splits, then stores these replicas in different geographic areas. Each multi-region configuration contains 2 regions that are designated as read-write regions, each of which contains 2 read-write replicas. It contains 2 read-write replicas. One of these read-write regions is designated as a default leader region, which means that it contains the database's leader replicas. Cloud Spanner also places a witness replica in a third region called a witness region. A voting algorithm is used to make decisions. Cloud Spanner provides clients with the strictest concurrency control guarantees for transactions, which is called external consistency. This is stronger than linearizability, serializability, strong consistency, and eventual consistency. The serializability guarantees transactions to execute serially while synchronized with the system. Strong consistency promises transactions to only execute while the dependencies have committed. Eventual consistency trades weaker guarantees for higher performances, like it's problematic because it means that readers can observe the database in a state that it has never truly been. Now let's create a spanner. In this demo, we'll learn how to create a Cloud Spanner instance, database, and table, add a schema, write and modify data, and run a query. In this demo, we'll learn how to create a spanner instance, database, and a table, add a schema to it, and manipulate some data, and finally run a few queries. So we're back here in our familiar Google Cloud Platform dashboard. And if this is your first time, please make sure that you have your billing set up and make sure that you're in the correct project. In my case, I'm in my storage demo project, and you can select that here, or you can press new project if you want to create a new project for this demo. So in my case, click on storage demo, and I'm in the correct project that I want to create the spanner database in. Now let's go to the navigation menu, and under storage we can see spanner. Click on this, and so first we have to enable the Cloud Spanner APIs. If this is your first time, we click on that and we wait. So now we can see that the API has been set up and we are ready to create our database. But before we can create a database, we need to create an instance, because a Cloud Spanner instance is what allocates resources that the databases use. So let's go ahead and press create instance, and here we can create a name. Here we can choose a name. I'm saying spanner demo, and I'm gonna choose a regional configuration with just one node. Now we could choose a multi-regional configuration. So we can choose a regional configuration for testing purposes, and we can choose any region here. So I'm going to select Europe North 1, and we can see the details here about this configuration that we chose. You could choose a multi-regional and choose a lot more nodes if you need to. So as we have discussed in our lecture, a minimum of 3 nodes is recommended if you are using a production environment. You can also see the cost here, which is not typical for most other products. The reason for that is Spanner is one of the more expensive products on Google Cloud Platform, and you really don't want to keep this up and running if you're not using it. Now let's hit create. And our instance has been created. So now we have an option to create a database. Click create database. For the database name, let's say DemoDB, and continue. Now we have an option to define the schema for the database. For now, I'm just going to ignore this and press create. So now our database has been created. Let's just go back and take a look at what actually happened. So here we are at our Spanner dashboard. This is our instance called Spanner demo, and in that instance we have one database called DemoDB here. If we click on this, then we can see that there are currently no tables in this demo. So if we want to create a table, we can click create table, and we can choose a table name. So let's call it singers. And here we can add columns by clicking on add column and creating the schema in a GUI fashion. Instead, we can also choose edit as text, and we can type in the DDL statements here, which is what I'm going to do. So here I have my code for creating a table called singers. with with 5 columns. Singer ID is the primary key here, and this is the same example that we have seen in the lecture. So let's go ahead and press create. And now we have our table here. Again, we have our instance, database, table. Now we can see the schema for this table right here, or we can also see the equivalent DDL right away. Also, there are 2 more tabs here, indexes, so we can see that if there are any indexes that are set up on this table. And finally, we have data. So with the data tab, we can manually insert data into this table. So if we click on insert, we can add the data for each column here. The primary key, the date, first name, last name, and any bytes. So let's just add some quick data here. And press save. So now we have 1 row in this table. Now if we want to query this, table, we can click on query here and then type in your SQL statements here. So we can just do something like select star from singers and run query, and we'll get our data here. Again, this is a very simple example, and typically you wouldn't be loading data into a table like this row by row from the GUI. You can also edit the data in this table by selecting the row and hitting edit, or delete the row by hitting delete. And finally, you can delete the database by selecting the database and pressing delete. And when you do, you have to type in the name of the database. In this case, it's DemoDB. And the database is gone. So now let's clean up the instance as well. So we select the instance and then delete instance. And in a similar fashion, we have to type in the name of the instance, press delete, and it's gone. Again, it's important to clean up and delete your spanner databases and instances because they will run a pretty high cost, and your free tier will evaporate if you keep the spanner running. Cloud Spanner enables you to query databases using declarative SQL statements. Cloud Spanner's SQL compiler transforms a SQL statement into a query execution plan, which is used to obtain the results of the query. A query execution plan displays the cost associated with each step of the query. Using these costs, you can debug query performance issues and optimize your query. When Cloud Spanner measures CPU utilization, it organizes tasks into high priority and low priority tasks. If necessary, Cloud Spanner stops all low priority tasks and allows high priority tasks to utilize up to 100% of the available CPU resources. While low priority system tasks can be delayed in the short term, they must run eventually for optimal performance. The available metrics are the rolling average 24 hours, high priority, and total. Based on the latency of each request, Cloud Spanner groups these requests into percentiles. We have the 50th percentile latency and the 99th percentile latency. Each one is a maximum latency in seconds for the fastest 50% of all requests and the fastest 99% of all requests, respectively. The 50th percent latency is sometimes called the median latency. For example, if the 50th percentile latency is half a second, then Cloud Spanner processed 50% of the requests in less than half a second. For the 99th percentile latency, for example, if the 99th percentile latency is 2 seconds, that means that Cloud Spanner processed 99% of the requests in less than 2 seconds. Cloud Spanner provides clients with the strictest concurrency control guarantees for transactions, which is called external consistency. External consistency states that Cloud Spanner executes transactions in a manner that is indistinguishable from a system in which the transactions are executed serially and the serial order is consistent. This is stronger than linearizability, serializability, strong consistency, and eventual consistency. Linearizability is a property of concurrent objects that supports atomic read and write operations, but does not say anything about the behavior of the transactions. Serializability guarantees transactions to execute serially while synchronized with the system. Strong consistency provides transactions to only execute after the dependencies have committed. Eventual consistency trades weaker guarantees for higher performance. This is problematic because it means that readers can observe the database in a state that it was never truly in. Cloud Spanner provides some of this functionality. Cloud Spanner provides something called stale reads, which offers a similar performance benefit of eventual consistency, but without trading for weaker guarantees. Okay, let's take a look at an example of eventual consistency. So here we have a person called Joe. He checks the weather report and learns that it's going to rain tomorrow. Joe tells his son that it's going to rain tomorrow. Now, Joe's wife tells their daughter that it's going to be sunny. And then Joe tells his wife that it's going to rain. So now, Joe's wife has given the wrong information to her daughter. So initially, we did have two separate sources, Joe and Joe's son, with the correct information. However, before that information was propagated to Joe's wife has given the wrong information to their daughter. Now later on, Joe's wife did get updated with the correct information, but Joe's daughter is now gone off with the wrong information and does not have the correct weather report. The reason why so many NoSQL systems have eventual consistency is because most of them are distributed. And in order to achieve a good amount of performance, you can't really have strong consistency without spending an exponential amount of money on hardware. This example was taken from Stack Overflow. Now let's take a look at a real-world example. This is from a Google Cloud Next event. Here they showed that its ticketing system was processing about 500,000 ticket sales per minute. And the database behind that system was 80 terabytes, which was migrated at around a gigabyte per second. Finally, the database structure behind that system looks pretty straightforward, like any other SQL system. However, the tickets table has over 3 billion rows and still can be queried in real time while those ticket sales are happening.
For more details, check the link in the description. Learn with Whizlabs. Success certified.